Hello, everybody. So, welcome to virtual lecture for today, Tuesday. We are having virtual lecture today because I am still in New Orleans and I won't be back until Thursday. So, what's going to happen is that we'll go through half of this lecture today on video with the video lecture slash virtual lecture, and then we'll finish the other half of it on Thursday. So, this is chemical bonding. We're talking about a new unit now, and or not a new unit, but a new chapter. And so it's just going to be an extension of the chapter that we did before spring break. So let's go ahead and get started. I'll switch over to my presentation view now, and then we should be able to get this thing going. There we go. Okay, so chemical bonding, right? Lecture 13. So in this particular lecture, you'll be able to identify and describe the law of conservation of mass, identify and describe the law of definite proportions, describe Dalton's atomic theory and electronic shell distribution, which you talked about a little bit already in the last lecture. Also describe what ionic compounds are, and ionic bonding is, and what Lewis structures are. And then I think we're going to stop there for today, and then we'll come back on Thursday live, face to face, and we'll finish it off with the identifying of single, double, and triple bonds, and then describing covalent and bonding covalent bonds and covalent compounds, and comparing, contrasting what ionic and covalent compounds are, and then electronegativity, polarity, Vesper, and then describing water and its properties. So we'll probably stop right around here. So, um, can you see my mouse? I don't know if you can or not, but I think you can. So we'll stop right about here for today. So let's go ahead and get started. So what is the law of conservation of mass? The law of conservation of mass was discovered by my guy, Antoine Lavoisier. Remember him? I think I told you about him. He was a French chemist who was very correct in a lot of his theories, but he was very active during the French Revolution, so he ended up getting like guillotined, his head cut off because of because his the people of the French Revolution weren't really having his theories, right? So they cut his head off. But it turns out that he was right. And so, really, what the law of mass conservation says is that matter cannot be created or destroyed. And so, you can look and see in these two slides, or these two images right here. You have a candle that's been lit inside of a glass flask here, or glass bulb, and it's burning, and there's a mass right here that's the same weight of the whole thing right there. And so as the candle burns, right, it will start to shrink in size, but for some reason the mass doesn't change. And the reason why the mass doesn't change is because a lot of the candle that got destroyed or got melted actually turned into the gas that's inside of the bulb. So what that means is that in this chemical reaction, going from a big candle to a very small candle that got completely melted down, right? Even though there was a chemical reaction and you saw physically something change, uh, there was no actual disappearance or destroying or creating of any matter because it just changed. And really, what happened here is that the candle, as it melted, it also consumed the oxygen in the atmosphere that's inside of the bulb, right? And so then everything started filling up with smoke and carbon dioxide inside. No carbon, yeah, carbon dioxide inside, and water vapor inside, because that's usually what the products of a fire is. And so, but regardless, you have a very a chemical reaction happening in one bulb, right? And it's almost finished now, right? In this bulb, but in the second bulb here, but it still weighs the same no matter what. And that's really the the crux of the law of conservation of mass. Matter cannot be created or destroyed, which is an extension from the law of thermodynamics. That's energy can't be created or destroyed; it can only change. So go ahead and scan this QR code and answer this question, right, for attendance. Which of the following is not true about the law of conservation of mass? Is it A, no detectable change in the total mass occurs during chemical reaction? Is it B, if the total mass involved in a chemical reaction is precisely measured before and after the reaction, there's no difference, which A and B essentially say the same thing. And then it was discovered by Max Planck in 1774, or all of these are true. Okay, so answer this question. All right, so then there's the law of definite proportions. And so the law of definite proportions says that if you have a certain amount of one thing, like one chemical compound or one chemical species or whatever element, uh, and you combine it with another chemical element, um, they have to have the right proportions to make the right, like for all of it to be used up to make the combined compound, right? It's kind of like baking. You have to have the exact right, components of like sugar, flour, butter, eggs to everything. Or if you don't, it doesn't come out right because there'll be too much extra of something, right? And so in this picture here, you see that we're making a compound called copper sulfide, copper 2 sulfide. So we'll get 10 grams of copper metal and then 5.06 grams of sulfur. We'll combine it together in a chemical reaction, and we'll end up with 15.06 grams of copper sulfide, right? And so nothing's left over. If you have too much sulfur, then and here we have 2 grams, right? Extra of sulfur, then we get 2 grams of sulfur left over, and we still only make 15.06 grams of copper 2 sulfide. And then the same thing is true of even having extra copper. If we have 10 grams of extra copper and we combine it, we can still only get the 15.06 grams of copper sulfide, right? And then we'll have 10 grams of copper left over. And so in both cases, there's excess reagents, right? So in this second case right here, there's excess excess sulfur and limited amount of copper. And in this case down here, there's excess copper and limited amount of sulfur. So the fun thing about this is that notice how we start out with 15 grams of copper and we end up in 5.06 grams of sulfur, and then we end up with 15.06 grams of copper sulfide. Like you add these numbers together, and you get the total grams of the entire compound. And so that actually confirms the law of mass, the law of conservation of mass, right? Matter cannot be created or destroyed. And it's also the reason why you end up with leftover stuff at the end too, for those excess and limited ones of this one and this one, right? The mass is still conserved with all that stuff. That's why you always get stuff left over. So this brings me to Dalton's atomic theory. In 1803, John Dalton proposed 3 hypotheses to explain the law of mass conservation, and then also the law of definite proportions. He said that each element is composed of the small individual particles called atoms. We talked about that already before in the but the atomic physics section of our chapter that we did a couple weeks ago, or a couple months ago, I think. And excuse me. And so an extension of this is that at least a part of his atomic theory says that atoms are identical for all elements of that atom, right? Sorry, atoms are identical for all atoms of that element. So a copper element, like an atom of copper, will be the same as all other atoms of copper, or an atom of carbon will always be all the same as another atom of carbon. Number 2 says that a chemical combination is simply the bonding of a definite number of atoms to make one molecule, and so a given compound will always have the same relative numbers of atom types. And the last one says that no atoms are gained, lost, or changed in identity during the chemical reaction. They are just rearranged to produce new substances, and that's a big thing right there. All right, elements are all the same, right? Of the periodic table, they all stay the same. What happens that makes each molecule different is that the atoms in the molecule actually just change or rearrange, right, in their organization, and so that is what gives us new substances when we have chemical reactions. And so these 3 atomic theories, or this theory with these 3 postulates, as we call them, are the modern cornerstone of chemistry. It's what really dictates how we teach chemistry today, because it works really well. So we talked about this already before, but we'll discuss it a little bit more now. When you look at the periodic table of the elements, all the elements are arranged in such a way that their group numbers represent the number of electrons they have in their outermost shell, right? And so when you look at the periodic table and you see group 1 elements, so this is group 1 right here, 1A is group 1, they all have one electron in their outer shell, right? One electron in their outer shell. Everything that's in group 2 has 2 electrons in their outer shell, okay? Group 3, 3 electrons in their outer shell. 4, 4 electrons. 5, 6, 7, and 8, and so on. The only exception to this is hydrogen and helium. Helium, because helium only has 2 electrons, and so that's why it doesn't have even enough to get to 8. So, but even then, its outer shell has 2. And I think I mentioned this before, but I'll say it again. Elements, they want to combine with each other so that they can have 8 electrons in their outer shell. And so everything that's in group 8 right here, right, has 8 electrons in their outer shell, except for helium, because 8 gives them a full outer shell. And all elements want to be as full, right? They want to be happy, they want to be full. And so they all want to be like group 8 elements, which is the noble gases, right? Because all the noble gases have a full outer shell. That's the reason why most noble gases don't interact with a lot of other elements, because they already have enough and they don't need anything else, right? But in the case of something like lithium or sodium right here, they've got one element, or sorry, one electron, right, on the outer shell that they can really get rid of easily, right? And so to get to a full outer shell of 8. And getting to a full outer shell of 8 means the rule of the octet rule, right? Where all elements or atoms want to have a full outer shell of electrons. Again, the only exception to those are the 2 that can't even have that many electrons, and so um, uh, things like that have less than 8 electrons won't have 8 in their full outer shell. They're just trying to get to 2 electrons because it's their full outer shell will be their first shell that only has 2 electrons in it, right? So we'll take, for example, sodium right here that has 1 electron in its outer shell. It has 8 in the second shell. So if it gets rid of that 1 in its outer shell, then its new outer shell will have 8, right? And it can easily do this. It can easily do this because it can get rid of this electron so easily and give it off to something over here, like something in group 7. Because things in group 7 have 7 electrons. Sorry, they have 7 electrons in their outer shell. And so you take a sodium, right, that has 1 electron, give that electron to a chlorine, right? And then chlorine gets 8 electrons in its outer shell, because 7 plus 1 is 8. And then sodium loses that electron, and so it has 8 in its outer shell now. And then you make the compound sodium chloride, which is table salt that we can't live without, literally, right? And these happen very commonly. Elements or atoms in group 2, they have 2 electrons in their outer shell. They'll happily bind with things in group 6, right? So that they can get rid of their electrons, and group 6 will receive those 2 electrons, and then both will have a full outer shell. If there's one thing I want to say, and I always want to, I'll keep on saying it, it's that the guys in Group 7, they are very greedy, and they will do anything to have an electron so they can fill their outer shell. And so they're quite insidious, especially chlorine. Chlorine is so bad, so insidious, that it will steal an electron from a kitten. And in this case, sodium is the kitten, and it steals an electron from sodium. And so chlorine is the gas that that was used in World War I as a chemical warfare agent. It becomes hydrochloric acid in your mouth and your throat because it takes electrons from water. So that's how people die from chlorine. And then also in a show called Narcos, there's this one part where these guys are trying to get rid of some chlorine gas that came off of their synthesizing and their workup of like cocaine and or extraction of cocaine from coca plants. And the way they got rid of it was they thought they could just pipe it down into like the toilet, but the toilet was connected to other apartments, and the gases of the chlorine just went into the other apartments and killed everybody in the apartments, and everybody got that chlorine poisoning. So chlorine's terrible. Chlorine's insidious. It will steal an electron from a kitten, and in this case, the kitten is sodium. So what is ionic bonding then? Well, there's 2 types of bonding. We'll talk about ionic bonding here, and we'll talk about the other one, which is covalent bonding in the next on Thursday, right? But the biggest difference is that in ionic bonding, there's actually a transferring of electrons, right? So the metals will actually the metals will actually lose electrons, whereas the nonmetals will gain electrons, right? And I'll show you what I mean in a second. And then in covalent bonding, which we'll talk about later, that's a sharing of electrons, not a transfer of electrons, right? So just remember that transferring electrons is ionic bonding, right? And then so the metals always lose electrons, right? Whereas the nonmetals will gain electrons, okay? And so what happens when a metal or a nonmetal loses or gains an electron is that they become charged. So here's a neutral atom, right? Here's a neutral atom, any atom, right? If this atom happened to be a metal like sodium and it lost one electron, it becomes this thing called a cation. Whereas if it actually is a nonmetal like chlorine, like a gas, it gains an electron, it becomes an anion, right? So the way I like to use this for as an example is that, especially since it works well with my whole cat thing, is that metals are cat ions. They become cat ions, and these cat ions are positive because cats have paws, right? So positive for cat ions, right? And then, of course, since cat ions are positive, the only other charge is negative, so anions are going to be negative, right? So a cat, or sorry, not a cat, but a chlorine will steal, right, an electron from a kitten, a cat, right, which is a cat ion, and it's positive, and that's a metal. So remember that's generally what happens. Metals that are on the left side of the periodic table, they'll lose their electron and they become positive because they're cat ions and cats have paws, right? Whereas anions will gain electrons, which are things on those are usually the gases, and they're on the right hand side of the periodic table. They'll gain electrons, they'll become anions, and they're very, like I said, insidious. They'll just take electrons like chlorine. Will take an electron from a kitten. So next question. Ionic bonding is the result of what in regards to electrons? Is this a sharing of electrons, a transferring of electrons, excited electrons, or promoting electrons? All right, so go ahead and answer that question. So I kind of alluded to this already, but the periodic table is arranged in such a way that the group numbers actually not only tell you how many electrons are available in the valence shell, or also known as the outer shell of the atom, but it also tells you what the charge of the atom will be once it loses or gains an electron. So atoms that are in group 1 will always lose one electron, meaning they will always be a positive charge when they lose one electron. Atoms in group 2 will lose 2 electrons, and so they become to positive 2 charge, right? Because they lost 2 electrons. Let's jump all the way over to the other side, which is the nonmetals over here. And so again, group 8, which is the noble gases, they don't lose anything, right? They like to keep they have 8 electrons in their outer shell, except for helium that has 2. Either way, all full. They don't want to lose or gain electrons, so they're not going to be charged at all. Whereas remember that group 7 right here, chlorine, the one that's so insidious, the guy that's so insidious that was still an electron from a kitten, is in group 7. They steal one electron from metals, right? All of them will steal one electron from metal, and so that one extra electron makes them one -1 charge. Group 6 atoms, right, will steal 2 electrons, making them -2 charge, and then so on with group 5. They steal 3 electrons, and so they'll become -3, right? So the easy way to figure out the charges for the non-metals, right? It's easy for the metals because the metals charges are going to be the same as the group number. Whereas for non-metals, it's a little bit different. It's not hard though. All you have to do is know that 8 electrons are what all these people want, right? And so you take the number, the group number, which is 7, for example, for group 7, and subtract 8 from it, and it gives you -1, and that gives you the charge. And then for group 6, same thing. 8, it's group 6, take the group number, subtract it by 8, and you get -2. And then group 5, take the group number, which is 5, subtract 8 from it, you get -3. And that's how you get the charges for all the metals. And so this is just another showing you of the different charges. Again, group 1, 1 charge, or +1 charge. Group 2, +2 charge. These are all the metals, right? And then +3, group 3, +3 charge, right? These are still metals like aluminum, right? And then we jump over to this side here, which is the nonmetals on the right hand side. And so, of course, group 8 has a full shell, so they don't have a charge, they don't care. Whereas group 7 is a -1 charge, because group 7 -8 is -1. It needs 1 electron to be happy, so it's going to gain, it's going to steal it from metal like sodium. Things in group 6, right? 6 minus 8 gets you -2, and that's that charge, which means that these guys here in group 6 need 2 electrons to be happy, so they will always steal 2 electrons, becoming a -2 charge. And then the same thing is true of group 5, except for group 5 is -3, because they need 3 electrons to be happy. So let's talk about table salt. I always use table salt as the example here, right? And so here's sodium, and sodium at this point right now has 11 electrons, and it really wants to lose that 11th electron, that 1 extra electron, right? So that it can have a full shell. So it will lose that 1 electron, making it only have 10 electrons now, right? And it will lose that electron. And guess who takes it? Chlorine does, right? And chlorine, here's the chlorine atom right here that has 17 electrons. And then it will steal or take the electron away from that sodium gave up, and then it will have 8 electrons in its outer shell. And now it's got a full shell of outer shell of 8 electrons in its outer shell, right? So those are, you can see it by numbers here. Here's a sodium atom with an extra 1 electron. It gets rid of that 1 electron, so now it's got a full row on, right? It's also a +1 charge now, right? And then here's chlorine right here, and it accepts an extra electron from sodium, right? And so now it's got 8 in its outer shell. It's happy, and that's called the chloride atom ion, right? So notice that when a nonmetal right here, for example, chlorine, receives an electron or steals an electron, it changes its name to chloride, right? It's kind of like getting married. Sodium and chlorine got married, and then so chloride had to change its name, which kind of makes sense though, since chloride did the stealing to begin with, right? So again, just remember, sodium is a metal, it loses electrons, whereas chlorine, it will gain electrons, and when it gains an electron, it turns into the chloride ion, and ions are charged. And so what actually happens physically in the reaction? We have sodium metal right here, we got chlorine gas here, and then when they combine with each other, they actually form this salt crystal right here. And these crystals are very well arranged, and they sit right next to each other to maintain their balanced charge, right? And then also have 8 electrons in the outer shell. That's like the best of everything right there. An element or an atom wants to have not only 8 electrons, but also neutral charge when they're together. So together, sodium and chloride obtain their goals of being both 0 charge, and then also having 8 electrons. 0 charge when they're together, only when they're together, and then 8 electrons in their outer shells, or full outer shells, right? And so that's basically how it goes. Let's see here. I think I have a video coming soon. Okay, so we're just going to take a quick look at a salt crystal real quick. And so here, a salt crystal, you can see that it's very well arranged. Every other atom is a chlorine, and every other atom is a sodium. And so one part of the crystal that has one partner with another partner, chloride with the sodium, that's called a formula unit, right? And so note that it is actually impossible to associate any one sodium with any specific chloride. They all sit together, right? And so this whole thing right here, this is called an ionic compound, right? This is not a molecule. Molecules are actually nonmetals only. So we call this ionic compound because it contains a metal and a nonmetal, right? Which is sodium and chloride. All right, so I have a video here for you guys to watch real quick, and it's kind of a fun video. So let's watch it.
Sodium. Symbol Na. 11 protons and 11 electrons, arranged in shells as 2, 8, and 1. Sodium is an alkaline metal. Like all the elements in this group, it's desperate to get rid of that extra electron.
If you cut it quickly,
I should see some
you should see a silvery surface inside. Indeed, wow.
It slices like cheese, but it's actually a soft metal. Teo's offered to put on one of his favorite sodium demonstrations. What happens when the pure element dumps its outer electron in a violent altercation with ordinary water? He insists we wait until nightfall, when the reaction will be most spectacular. Kids, do not try this at home.
The whole purpose of this contraption is just to dump it into the bucket of water?
Yeah, it's a sodium dumping machine.
All right, let's give this a try. Here we go. Nice. Boom!
What we're seeing is what happens when sodium's extra electron tears apart water molecules, releasing flammable hydrogen gas, the H in H2O, which explodes when it mixes with air. The next day, Teo takes it up a notch. As if sodium plus water weren't violent enough, now he wants to combine the same deadly sodium with another lethal element, chlorine, one of the halogens. The result, he claims, will be a tasty flavoring for a net full of popcorn?
Isn't chlorine deadly poison?
Absolutely. I mean, chlorine, they used it as a poison gas in World War I.
It'll be perfectly safe when these two deadly ingredients combine.
I didn't say that. I said that after they're combined, the result is perfectly safe. The actual process of combining them is fraught with difficulties.
Okay, and that's why we're dressed up like miners here.
First, a hunk of sodium in a dry metal bowl. Then, a jet of pure chlorine. Surprisingly, no explosion. Somehow, when these two bad boys of the periodic table come together, they calm down. At the atomic level, sodium, an alkali metal, had an electron it didn't want, and chlorine, a halogen, wants desperately to grab an electron. Once the handoff was complete, both atoms wound up with full shells, making them stable, and able to join together to form a crystal compound we can't live without. Sodium chloride, table salt.
Now, I don't exactly see, like, a pile of salt anywhere.
Now, the salt, most of it went up in the smoke. It went in the popcorn.
Tastes like salt. The good stuff. Fresh.
Fresh
Only
salt.
the freshest salt at Teo's farm.
Teo's backyard reactions have given me a crucial insight. How elements come together to form compounds is all about electrons.
So yeah, that was a fun video to watch. So let's keep going, because I think I have another video for you to watch.
Sodium.
Oh,
Symbol Na.
there we go. Here's the next video. So this is the same guy, and he actually did this demonstration, and it didn't go so well. So I wanted you to see this video too.
This is one of my favorite experiments. Supposing you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff. You got to make it yourself. Well, how are you going to do that? Salt is sodium chloride. Sodium is a metal that explodes on contact with water, and chlorine is a deadly poison gas. They actually used it in World War I as a poison gas. But if you take a bowl full of molten sodium and you blow pure chlorine gas into it, you get a fire, and the smoke coming off of that is pure salt. So we hung some popcorn over it, salt the popcorn with nice fresh salt. And it worked great. We got some good shots that we used in the magazine. Then, turns out, the net started melting, and it actually dropped the popcorn into the molten sodium. Sodium exploded, and we got popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all the right safety equipment. And it made some really good shots that we could use also.
Fun stuff. Okay, so I think we're getting close to the end of what I want to talk about today.
This is one of my...
There we go. Okay, so here's your next question. What do the elements in group A, 1A of the periodic table tend to do with their valence electrons? Do they like to lose one electron? Do they like to lose 2 electrons? Do they like to gain 1 electron? Or do they like to gain 2 electrons? So go ahead and answer that question. All right, so Lewis dot structures, what are they? Well, Lewis dot structures are generally just pictures of atoms, showing what their valence electrons are, right? So for example, in group 1, the Lewis dot structure of everything in group 1 has a 1 dot, because that means that it has 1 electron in the outer shell that it wants to get rid of. Group 2, same thing, right? There's only 2 dots because it has 2 electrons it's trying to get rid of. Group 3 has 3 dots, which is 3 electrons in the outer shell, right? So here's boron and aluminum. Group 4, same thing, 4 electrons in their outer shell. Group 5, they have 5 electrons in their outer shell, so they need 3 to get to 8. And then group 6 has 6 dots here for 6 electrons, which means it needs 2 more to get 8. And then group 7 has 7 electrons in the outer shell, which is 7 dots, and it needs 2 more, or needs 1 more to get 8, right? And of course, it's going to steal it from somebody over there on the metal side, right? And then, of course, everything but helium in group 8 has 8 electrons, right? And so you see 8 dots, and that's literally what a Lewis dot structure is. It just shows the the number of electrons in the outer shell. So look, if you look at the example of sodium chloride right here, chlorine begins as an atom that looks like this, right, where it has 7 dots in its outer shell, and then when it steals that electron from sodium, it becomes negatively charged, but now it has 8 electrons or 8 dots in its outer shell, so it's happy. The opposite happens with sodium, right? It loses this electron and becomes positive, but it has nothing in its outer shell now, right? Because it only has its inner shell that has a full shell, which is 2 electrons, because sodium only has, not 2, sorry, has 8 electrons now, right? And so it becomes a positive charge because it lost this extra electron on the outside, and now it has 8 electrons in its new outer shell, okay? That's what a Lewis dot structure is, right? And so when an atom becomes when an atom becomes an ion, right, because it either gained or lost electrons, it becomes what we call isoelectronic with other atoms. And so isoelectronic just means the same number of electrons. And so when we say same number of electrons as other atoms, we're talking about the same as the noble gases. For example, aluminum here, right? It really wants to get rid of these 3 electrons, right? It's got 3 electrons extra. It wants to get rid of them because it's a metal, right? When it loses the 3 electrons, it becomes an ion, of course, and it only has 8 now. It will now have 8 electrons in its outer shell, in its new shell, which means it's happy because it lost these 3 extra ones that it doesn't need. And when it does that, it becomes just like neon, because neon is the same thing, right? It has 2 in the first shell and 8 in the outer shell. Same thing happens with sulfur. Sulfur needs 2 electrons in its outer shell to make its outer shell have 8 because it's a nonmetal. And so when it gains those 2 electrons, it will become the same number of electrons as argon, because argon has 2, 8, and 8 as well, right? And so you can do that with any of the elements and figure out what its isoelectronic partner is. And every element or every atom's isoelectronic partner will be a noble gas, right? So then how do we write structures, not structures, but how do we write what are these called? Chemical formulas is what they're called. Thank you. So the way we write chemical formulas is super easy. If you look at, like, for example, lithium here, right? Lithium, remember, is in group 1, so it has a positive 1 charge. And then oxygen is in group 2, so it has a negative 2 charge. We can write down Li for lithium and then oxygen, right? O for oxygen. But how do we know what the subscripts are going to be for their formula? It's really easy. All you have to do is take the charge, the number from the charge of each of the atoms, and then switch them. So the 1 right here from lithium just comes down to be the subscript of the oxygen. And so in chemistry, when nothing is there, we just assume that it's 1. And then the 2 from the 2 charge, negative 2 charge of oxygen will come out here and be lithium's charge, right? And then so, not lithium's charge, lithium substrate, which means there are 2 lithiums, right? So that's one thing atoms can do too. Since oxygen has a negative 2 charge, it needs 2 lithiums to be happy, right? Kind of a threesome for it to be happy, right? Because 2 1 positive charges will balance out a single negative 2 charge, right? And so that's when it's happy. And it will get those it will get the electrons it needs to fill its outer shells, and then both two lithiums will be happy because they will both lose an electron to that oxygen, and they'll be happy, right? So here's some other examples here too. Here's calcium chloride. Calcium has a charge of +2, and so it needs two negative charged chlorines to become neutral charge, right? And also have 8 electrons inside our shell, right? Because remember, sodium's in group 2. Calcium's in group 2, so it has a plus. It's got a it becomes a +2 charge. We also have these things called polyatomic ions too. For example, this one's phosphate. It's got a negative charge. The way we can figure those out is because we can go through and figure out the charge of each one of these atoms. This phosphorus, these 4 oxygens, and then we can combine them together, and that will give us a charge of -3 for phosphate. There are plenty of polyatomic ions, but don't worry about them. But just know that they exist. And so since phosphate has a -3 charge, right, and then calcium has a -2 charge, and we switch the numbers, right, so the +2 charge that's from calcium comes over here to be the number, the subscript for phosphate, and then the -3 charge comes over here to be the subscript for calcium, and that's how you get the formula for calcium phosphate, right? So what are some properties then of ionic compounds? So they're very strong, right, because it's opposites attract basically, and so they're always crystalline structures, and they also have very high melting points and very high boiling points. You know this because you can throw salt into a frying pan and it will not melt, and it's because it's an ionic compound. But if you throw sugar into a frying pan, what happens to it? Heat it up, it melts, and not just melts, but eventually it will become caramel, right, and then burn completely into just dust, carbon dust, and that's because sugar is not an ionic compound, it is a covalent compound. So that's a big difference between ionic compounds and covalent compounds. Ionic compounds have very high melting points, and they have very high boiling points, right, because they form these crystalline solids. Ionic compounds also will conduct electricity, right, especially if you have them dissolved in water. That's why you cannot throw a running hair blow dryer, right, into a bathtub, right, because if you did, you'd electrocute yourself, because bath water is not clean. It has salts in them. If anything, it has salts from you because you sweat while you're in the bathtub. You don't feel like it. You are, because it's it's all water. But if it's hot enough, you're sweating, and you're adding salt from your sweat into the water, and it electrocutes you. And salt, of course, is ionic, right? So the interesting thing is that if the compound is a solid, it will not conduct electricity, right? So if you just have like a pile of salt and you try to make some electricity go through it, it won't go through it because the ions can't move it can't move very well in a solid. But melted ionic compounds will definitely conduct electricity, right? And then also ions that have been dissolved in water will conduct electricity as well, just like salt water. And that's what you see here in this little picture. We have water with some salt in it, right? And so if you attach a light bulb to it and a battery, you can see that it conducts electricity. Now, if you had done that with sugar, it would not work, right? Or if you just had, a pile of salt in that beaker, it would not work either. It has to be either melted salt or salt that's dissolved in water. And then so we do have some other some names. So I put this on here because a lot of people look at the periodic table and they get confused as to why some elements have their initials as their first name, right, as their name, and some don't. And so these are examples of ones that don't. Copper is actually, you would think that it would be Co or something like that, but it can't be because cobalt is Co. So the Greek name or the Latin name, I can't remember if it's Greek or Latin, will actually have for copper is actually cuprous, right? Coop, right? And so turns out copper can actually either copper can either lose 1 electron or lose 2 electrons. So it has 2 states it can be in, right? And so the state where it has lost 1 electron is called cuprous. In the state where it's lost 2 electrons, it's called cupric, right? Gold, same thing, except it's 1 and 3, right? Gold, back in Latin days, was actually called aureus. And so aureus is the gold that has lost 1 electron, and then auric is the gold that's lost 3 electrons. The most common one is probably iron. A lot of people get confused because iron's symbol on the periodic table is actually Fe. not like something like IR like you would think. But the reason why it's not IR is because another one is IR called iridium, right? So we have to use something else. So the old name for iron is ferrous, and so iron that has lost 2 electrons will be called the ferrous ion, whereas iron that has lost 3 electrons will be called the ferric ion, right? And then chromium. The only difference here is that chromium has it looks like chromium because it's Cr, but it's missing the H, so that's why it's not the exact initials, right? But so losing 2 electrons means becoming chromous, and losing 3 becomes chromic. There we go. And so there are other examples too that I haven't really that I don't have on here, but I think I talked about in the last lecture. Like sodium's real name is actually natrium. That's why it's Na, right? And then potassium's real name is like kalium or something like that, and so that's why it's K. So just things to be aware of. I think that's all I want to talk about in this particular lecture. We'll come back on Thursday and start on covalent bonding. So thank you.